Well, hello and welcome. In this video, I'll be covering section 4.4, which is over theorems about zeros of polynomial functions. My goal for you by the end of the video is to be able to find a polynomial with specified zeros, and to be able to, from a given polynomial function with integer coefficients, find the rational zeros as well as other zeros if possible. So we'll go ahead and start with a couple of basics about polynomial functions. First of all, the fundamental theorem of algebra, which states that every polynomial function that has a degree of n, with n being greater than or potentially equal to 1, it must have at least one zero in the set of complex numbers. So it basically just would mean that no matter what, if I set it equal to 0, I should be able to get a solution that is either real or potentially imaginary. When it comes to writing polynomial functions when we're given zeros, ultimately if I had a list of zeros, in this case we're utilizing subscripts, so C1, C2, C3, all the way up to Cn, we would be able to write at least the factored form by just doing x minus each of those zeros inside of sets of parentheses. If there happen to be any multiplicities, I would put powers on the outside of the parenthesis, and then I just list it out as a product, potentially having a coefficient, which we're representing with the a subscript n in front. But when it comes down to it, ultimately if I wanted to come up with what the polynomial was, I would then just start picking away at it and multiplying two sets of parentheses at a time until I finally eliminated all the parentheses when it's all said and done to get it into that polynomial form. So again, remember, factored form is the one where you have a list of parentheses multiplying together, whereas polynomial form is when you have all of those parentheses that have been expanded to where now it can be rewritten in what would be considered descending order, where your highest powered term would be first, and then the powers count down as you go. So this first example is to just basically to provide some context, or at least a visual, for what that last slide was mentioning. So for this one, part A, if we go ahead and at least get the startup taken care of, what's nice is when it just says find a polynomial, or write any polynomial that has these zeros, the coefficient or the leading coefficient that you can have out front ultimately can be any number you want it to be. So for all of the examples I'll try and keep it as simple as possible and just keep that leading coefficient a 1, unless I felt like maybe a number would be better to put in front that would maybe eliminate some fractions, like with part C. There's a little bit better way of dealing with that, but we'll get there when we get there. So each of these, again, remember, if I have these listed out as zeros, what that theorem before said is I could just basically do x minus each of those zeros and just set up a parenthesis for each. So if we look at part A, it's got 4 different numbers, so I'm expecting to write 4 different parentheses. I'm going to go ahead and actually focus my attention on the x equals 0, because ultimately if I had x minus 0, that would just be a plain x in front. So I'm just going to write it as an x in front of all of these parentheses, and pretty much I'm going to wait for that one to the very end when it comes to the actual multiplying out. Now as far as the other zeros, x minus and negative 1 would actually switch to x plus 1. Next one, x minus 2, doesn't really need to change. And then the last one, x minus 4. So when it comes to actually multiplying these things out, I'm just going to take 2 parentheses at a time. So I'm going to take the last 2 and actually multiply those out. I'm going to go ahead and leave the first 2 kind of untouched. But now if I distribute through the terms, I've got x that's going to distribute through to give me x squared. Then I'd have a minus 4x. But then there's going to be another like term from these two multiplying, negative 2 times x. So if I have a negative 4x and a negative 2x, really I could combine that and call it negative 6x. And then the last term would be the negative 2 multiplying with the negative 4, which would give me a positive 8. From here now I would distribute out the next 2. So if I distribute these 2 out, again, notice that the x that I have in front is just kind of staying there. I'm saving that one for the last one because that's actually going to be the easiest one to multiply by. So with this, I'll distribute through the x. So that's going to give me 3 separate terms. So if I do that, x times x squared would give me x cubed. X times a negative 6x would give me a negative 6x squared. And x times a positive 8 would give me positive 8x. Then I can move on to distributing the 1 through, which really is just going to rewrite all three terms from the second one, but let's just go ahead and see it. 1 times x squared is in fact that x squared. 1 times negative 6x would give me negative 6x, and 1 times a positive 8 would give me a positive 8. So at this point, notice we do have a couple of like terms that we could combine. We have a couple of x squareds as well as a couple of x's. So I'm going to go ahead and rewrite this one as really it's x times the x cubed minus 6x squared plus x squared would be a minus 5x squared. 8x take away 6x would give me a positive 2x, and then there's still the plus 8 at the very end. And now I'm to my last step, which is just distribute the x through the four terms that I now have, which then would give me x to the fourth minus 5x cubed plus 2x squared, and then plus 8x. And there we have our first expansion, at least for the example we have here. The next one I'm going to go ahead and set up, but this time notice it says it has a multiplicity of 2 on this negative 3, so how I account for that would be I'd put x plus 3, it was a weird 3, my apologies, x plus 3, but because of the multiplicity of 2, it's going to have a power of 2 outside. And then I'll move on to the next one, which is an x minus 5. And again, the reason the first one switched to addition is because technically it would have been x minus a negative 3, and minus a negative does turn into addition. So at this point, we could potentially just rewrite that first parenthesis actually out as 2 separate parentheses just to help with the expansion portion. And I'll go ahead and multiply those out first. So if I did multiply the x plus 3 with the x plus 3, that would give me an x squared plus 3x, so plus 6x in the middle. And then a 3 times 3 would give me a plus 9. And then I have the x minus 5 after that I still haven't multiplied by. But now I can go ahead and distribute things out. X squared times x, and then x squared times a negative 5 would be the next two terms. So this will give me, if I try and at least separate the two problems we have so far. So I've got x squared times x was x cubed minus 5x squared. Then I've got a 6x multiplying with an x, and then a 6x multiplying with a negative 5. So that would give me a 6x squared, and then a negative 30x. And then move on to the last term to distribute, which is the 9. I'll take it through underneath here. So 9 times x, so positive 9x, and 9 times negative 5, negative 45. So as far as like terms are concerned, there are a few with this one. So it looks like this would turn into x cubed plus a negative 5 plus 6 is a positive 1, so plus x squared. Negative 30 plus 9 would be a negative 21x, and then still the minus 45. Now on to the last one, which I prefaced a little earlier. This one has a fraction, so what we can do is if we set this up kind of similar to one of the shortcuts with factoring, I'll just go, once I get there, I'll describe it a little bit better. So the first one, x minus a negative 3 would switch to x plus 3. X minus 5. And then the last one, technically I could write as x minus 2/5. But just like we've done with that shortcut for factoring, I can take that 5. Since I could make a coefficient of 5 out front, I could just say I'm going to multiply that 5 through just the last parenthesis, and essentially it would turn that x minus 2/5 into a 5x minus 2. So I'll go ahead and write that a little bit cleaner underneath, and then it will just turn into, again, I'll need to find a way to multiply out each of these things. So I'm going to start with the last two. So that x plus 3 will just kind of stay in front. Here, if I distribute out, x times a 5x would give me 5x squared. Then I've got an x times a negative 2, which would give me negative 2x, but then as expected, the next term is going to be a like term, so we'll go ahead and figure that one out as well, which is negative 5 times 5x, which is negative 25x. So a negative 25 with a negative 2 would give me a negative 27x. And then a negative 5 times a negative 2, that would give me a positive 10. And now on to the last expansion I have to do. Just distribute the x through. and then distribute the 3 through after that. So if I were to list those terms out, x times 5x squared would give me 5x cubed. X times a negative 27x would give me a negative 27x squared. And x times a 10 would give me a positive 10x. Then on to distributing the 3 through. 3 times 5x squared would give me a 15x squared. 3 times a negative 27 is going to give me a negative 81x. And let's see, I've got a 3 times a 10, which would be a positive 30. So again, a couple of like terms. There's only the one x cubed term. There's a couple of x squared terms. I think I forgot the x squared on that 15. My apologies. So I've got negative 27 plus 15, which would give me a negative 12x squared. And I have a positive 10x and a negative 81x, which would really combine to give me negative 71x. And then the plus 30 at the very end. So as you can see with this, the setup is really the key to this, and then from there it's just having some patience and some due diligence when it comes to actually multiplying out these parentheses or distributing it out. But in the end, as you can see, all of these have turned into new polynomial form where there were no parentheses. I just needed to find a way to expand them out until it turned into that. Notice I've also written in each one what was considered the descending order, where the first term had the highest power, and then each term from there just decreased in value until I finally got to the last term, which potentially could be a constant. So now let's go ahead and talk about some of the, I guess, behaviors that happen with some of the zeros as I encounter them. So anytime if I'm solving for a zero of a polynomial function, if I come back with some zeros that happen to be non-real or happen to be something that is in the imaginary number system, what the format of those would be is essentially an a plus bi or maybe potentially an a minus bi. Now what's nice about this concept is if we happen to know that one of the zeros is something in one of those formats, a plus bi for example, then what actually is a guarantee is its conjugate, which is the a minus bi, would also happen to be a zero of that. And the reason that would happen is because if we think about where the I would have come from, I would come from taking a square root of a negative. Square root symbols are supposed to have that plus or minus symbol in front of them, which is why one time you use the addition, the other time you use subtraction. So one thing that, again, is kind of nice about any time you get a complex number, they will always happen in conjugate pairs. So the example we have here is if we happen to find, maybe by quadratic formula or maybe potentially by completing the square, that 2 plus 7i was a 0, then we would guarantee ourselves that 2 minus 7i would also happen to be a 0. So again, what the main big picture idea of this is anytime you get a non-real 0, you know that its conjugate pair will also have to be a 0 of that polynomial. So an application of how this could come to be, notice this one just says if you were given these zeros and you know what the degree of the polynomial happens to be, just state whatever the remaining zeros happen to be. So instead of having to actually set up and multiply out all of the factors to come up with a polynomial, we could just at this point, from the given zeros, find the remaining zeros that we have. So remember, the degree tells us how many total zeros we should have, counting both the real and imaginary ones. With this one, it's given us 2 zeros. One of them is 1 minus I, the other one is a negative 3i. So that's 2 out of the 4. There should be 2 more. Well, that's where the remaining zeros would be, since those were both imaginary or complex non-real numbers. It's just going to be, well, the other ones are going to be the conjugate pairs of them. So if 1 minus I happen to be a 0, then that's a guarantee that 1 plus I will be a 0. And then if the other one, we could really consider this like 0 minus 3i. If that happened to be one of the zeros, then the other 0 would be the conjugate pair of that, which is 0 plus 3i, which really is just 3i. So now notice that gives me a total of 4 zeros, the 2 that they gave us, and the 2 new ones that we found, for a total that matches now my degree. So if we go to the next one, notice this one gave us a real, so that one's just going to be its own 0, but then the other one, or other 2 actually for that matter, that they gave me, were those complex or non-real zeros, so they must happen in pairs, so the remaining zeros would be, if I have negative 2 plus I that was given, then negative 2 minus I has to be 1. And then the other one, if 0 plus 9i is 1, then 0 minus 9i, which really is just negative 9i, also would happen to be. So notice again that gives us 1, 2, 3 from the original, or what they gave us, and then 2 more from what we identified using the conjugate pair idea, which that then totals up to match the number that the degree was. So in this case, I now have all of my zeros identified. And now similarly to the complex zeros idea is we also could have now irrational zeros that follow that same idea, because again, irrational zeros would ultimately come from taking a square root inside of some form of solving, which then should accompany a plus or minus, or should have a plus or minus symbol accompany it. So if I have a plus c times b, in other words, maybe I was able to simplify the radical a little bit, but there still was not a perfect square left inside. If I have these irrational zeros, the ones that just cannot really be written in decimal format without rounding, then at that point I can go ahead and say that these also will happen in conjugate pairs. So as we have as an example here at the bottom, if we found that negative 3 plus 5 rad 2 happened to be a 0, then it's a guarantee its conjugate negative 3 minus 5 rad 2 would also happen to be a 0. So again, the key statement here is just the irrational zeros will also happen in what are called the conjugate pairs, which, just to again reiterate what a conjugate pair is it's the same two terms. We just change the operation in between from a plus to a minus, or potentially from a minus to a plus. So just like we did with the complex or non-real zeros example, in this case, if I told you what the degree is, which in this case, this problem says the degree is going to be 6, and I've given you some of these zeros. In this case, the zeros would be the negative 2 plus 5i, which then means, because that was one of those non-real ones, that means that negative 2 minus 5i would have to be another 0. So that's given me 2 total. If negative 2i was a 0, then that means positive 2i also should be, so that now has given me 4 zeros. And then the last one, 1 minus the square root of 3, well, that's a irrational 0, so its conjugate pair, 1 plus rad 3, also would have to be a 0. So notice that now gives me the 3 that they gave us, as well as the 3 new ones, the conjugate pairs of them, which is now a total of 6 zeros, which matches the degree. So I've now identified at least all of my zeros. So now that we've talked about how some of the zeros that we encounter will happen in conjugate pairs, now let's go ahead and talk about how we can maybe utilize this to come up with what an actual polynomial is that has those zeros. So part A here, notice they've given us a real 0, 3, and then they've given me an imaginary or complex 0, 2 plus I, which then means guaranteed 2 minus I was given, so 2 plus I would have to be the remaining zeros. So notice that gives me a total of 3, so I'm expecting this to have a degree of 3 when it's all said and done. But what we can do is fall back to the very first thing we talked about, which is we can, from zeros, actually come up with the factors, which in this case the first one would be x minus 3. The ones after this are going to be a little bit more complex because we actually need to group them in parentheses and put them after that minus sign. And then it would turn into, okay, now let's find a way to expand this, because this actually does want to know what the polynomial function is, not just necessarily the factored version of it. So I would always recommend that anytime you have those conjugate pairs get involved, you would just multiply those out. And I'll kind of show how that works here in this video, where if I just distribute it out, I'm going to keep things grouped inside of parentheses initially, and then I'll worry about kind of what that turns into in the following step. So if I go one term at a time, x times x would give me x squared. X times a negative parenthesis would just turn into a negative x times that parenthesis. So eventually I'll distribute the x through that 2 plus I. Then the same thing is going to kind of happen with this next one, a negative parenthesis times x. I could reorder and say it's a negative x times the other parenthesis, which for this one would have been the 2 minus I. Just multiplying this term with this term. And then the last one, I'd have a negative parenthesis times a negative parenthesis, which will turn into a positive. And then those two parentheses just multiply together. So 2 minus I times 2 plus I. So notice what's tricky about this is I ended up having to, I guess, distribute inside of the result that I just got. And then we're actually going to get some I squareds, which remember I squareds will actually get to be replaced by a negative 1. So I'm just going to simplify or clean up the inside here. X squared is really as good as that gets. I've got a negative x times 2, which would be a negative 2x. A negative x times I, which is a negative xi. Then I have a negative x times a 2, so another negative 2x. Now I have a negative x times a negative I, which actually is a positive xi. Which what's nice about that is the negative xi and the positive xi are going to be able to cancel out. And then the last one, I've got 2 times 2, which would give me a 4. I'd end up with a positive 2i, then a negative 2i, so those also will get to cancel. And then the last one would be a negative I times an I, which is a negative I squared. And again, remember the negative I squared, I technically could just say, well, I squared is negative 1, and minus a negative 1 would actually switch to plus 1. So really the plus 1 and the 4 will get to combine, and then the negative 2x and the negative 2x will also get to combine. So I've now got x minus 3 that would multiply with this quadratic of x squared. Negative 2x and a negative 2x is negative 4x. And then the positive 4 plus 1 from the I squared at the end would give me a positive 5. And so now distribute those two out, and what's nice is because I chose the conjugate pair to start with as far as my product is all of the i's have now gone away, so now everything is a lot more back to normal. So I've got x times x squared would give me x cubed. X times a negative 4x is a negative 4x squared. And x times a 5 would give me positive 5x. Then move on to distributing the negative 3, so I've got negative 3x squared. Negative 3 times negative 4x is positive 12x. And a negative 3 times a positive 5 would give me a negative 15 at the end. And just like every other expansion, we just look for combining like terms. I do have a negative 4x squared and a negative 3x squared for a total of negative 7x squared. I have a positive 5x and a positive 12x for a total of positive 17x. And then still that minus 15 at the very end. If I look at part B is going to have, it looks like it's given me 2 zeros, but one of them was a complex or a non-real one. So if negative 3i is a 0, then positive 3i also has to be a 0. So when it comes to the setup, go ahead and separate this a little bit. The setup for this one is going to be x minus a negative 2, so x plus 2, times x minus a negative 3i, which actually would turn into x plus 3i, and then x minus 3i, since the last one was technically a positive. So once again, take the two parentheses that are conjugates of one another. So in this case, those two. Leave the other one kind of alone for the time being. We'll save that for the end, but now I'll go ahead and multiply this out. X times x would give me x squared. X times a negative 3i would be a negative 3ix. The next one is going to be positive x times a positive 3i, so a positive 3ix. So those two terms actually look like they're opposites, so they'll cancel. And then I've got at the very end, a 3 times a negative 3, which is negative 9, but then also an I times I, which is I squared. So as mentioned here before, the negative 3ix and the positive 3ix will cancel each other out. And then this I squared that I have at the end right here, that's really like a negative 1. And if I have a negative 9 times the negative 1, that actually will switch to a plus 9. So I can now rewrite this as x plus 2 times, and then I've got the x squared now plus 9. And now I can distribute this out just like we've done before. So x will go through, then 2 will go through, list the terms out, and see what we get. X times x would give me x cubed. X times 9 would give me a positive 9x. 2 times x squared would give me positive 2x squared. And 2 times 9 would give me positive 18. So that's in a little bit of an order that's off because the power of 2 and the power of 1 were kind of backwards, so I'm going to go ahead and just do one last step of just rewriting it in that correct order or descending order. So I just kind of swap those middle two terms. Since it's addition, I can do that, and now it's something that's written in descending order. So hopefully this is making some sense as to how we can set these up and multiply it out. Obviously the part A, when you have a non-real zero that came back as a binomial, it was a little trickier with the parentheses that we had to deal with. But if you're just very deliberate with each of your steps and actually write them out and try not to do the mental math, hopefully it can prevent any of those simple maybe negative mistakes or multiplication mistakes that potentially can happen when it comes to expanding these things out. But again, notice it gets a little bit long and then eventually kind of combines together, and all of the I terms should cancel if you choose to multiply the two terms that have the imaginary parts with them right off the bat. Now we'll go ahead and transition on to the last thing to cover in this video, which is what's called the rational zeros theorem. So this is essentially what we will end up using for some of those. If I just said, here's a polynomial, factor it. Notice thus far I've had to provide you with a factor. This theorem here actually will allow us to, without knowing a factor, at least have a general idea of how we could start the process. So for the rational zeros theorem, what I'm actually going to focus on is this very last term, which we would call the constant, and then the very first number in front of the highest powered x, which again we call the leading coefficient. So essentially what we'll do is we'll think of all of the factors of the constant, and we'll list that out as all of the p values according to this formula. So notice we're going to denote this in a p over q format. And then we'll put it over all of the factors of the leading coefficient, which we'll represent using the q. And since I don't know whether they're going to be positive or negative, these will always have plus or minus symbols in front of them. But at least what it's doing is it's going to narrow down how many possible numbers to try to at least a couple of at least more intelligent numbers to try. Now that does not mean that every zero in my list will actually be a zero or anything along those lines. It's just telling me if there are rational zeros for the actual polynomial, they would have to come from that list. So it's basically just taking all of the numbers that exist and narrowing it down to a more finite set or a specific number of possible options to try, which is a lot better if you think in terms of if I only had maybe 8 options to try and I compare that with every possible number that exists. Definitely having it narrowed down to only 8 options would be a lot better than just completely pulling numbers out of nowhere. So to provide a visual for how the rational zero theorem ends up actually working, we'll go ahead and do this example. Notice this one just says to list out the possible rational zeros. It doesn't actually say anything about finding the zeros. So what we do is we basically start this process by listing out what are the possible p values and then what are the possible q values, and then I'm just going to create individual fractions from using one number from the top and one number from the bottom. So if we were to list out all of the factors of p, which again is going to come from the constant, I don't know if they're going to be positive values or negative values, so I'm just going to put plus or minus symbols in front of each number. And then I just start with, okay, if 12 is the number I have, let's just list out possible numbers that go into 12, which in this case 1 would be 1. I just kind of work my way up. 2 would go into it. 3 also would go into it. 4. And as soon as you have two numbers back to back that actually their product equals that number, so like 3 and 4 in this case, I can actually just go backwards through my list. What would 2 need to multiply with to get to 12? Well, that should be 6. And then what does 1 need to multiply with to get 12? Well, that would be 12. And notice again, I'm putting plus or minus symbols and separating them with commas just to kind of create this as a list, but also account for it could be positive, could be negative anytime. Then we'll move on to the q values, which are from the leading coefficient. So this number is a little bit smaller, so it's going to be factors of 4 that go in the denominator here. So 1 for sure goes into it, 2 goes into it, and technically 2 times 2 is 4, so then I can work my way back and go, well, what would 1 need to multiply with? Well, that would be 4. So the organization of this, instead of just throwing random numbers out, I would say start with the smaller numbers, work your way up, and once you have a pair of numbers that would multiply to equal it, just work your way back through and figure out what the second half, for example, with the top, what was needing to be multiplied with 2 to get to 12, that's where I could come up with a 6. Doing it that way oftentimes will make it such that you don't accidentally forget maybe that a number actually goes into it. But anyway, now what I'll do is just list these out where I take each number from the top individually and put it over a single number from the bottom. So 1 over 1 would give me 1. 2 over 1 would give me 1. Or sorry, 2. 3 over 1 would give me a 3. 4 over 1, and 6 over 1, and 12 over 1. So basically I took every number on top and put it over the 1 that was on the bottom. Now I'm going to go through and deal with the putting all those same numbers on top over 2. So that would be a plus or minus 1 over 2, so 1/2. Plus or minus 2 over 2, well that's 1. I've already got that number in my list. 3 over 2, that one I don't have, so that's new. 4 over 2 is the same as 2. I've already got that in the list. 6 over 2, that's the same as 3. I've already got that. And 12 over 2, that would be 6. I've already got that. So I'm pretty much done with the over 2. Now we'll move on to the over 4. So plus or minus 1 over 4, that's a new number. 2 over 4 is 1/2. I've already got that one. 3 over 4, that one's new. 4 over 4 was the same as 1. Already had that. 6 over 4 is the same as 3 over 2, so I already have that. And then 12 over 4, that's the same as 3. I've already got that. So my list of possible rational zeros to try synthetic division with are essentially that long list. In this case, it doesn't seem like that really narrowed it down a lot. But if you were to think in terms of how many numbers truly do exist, that definitely is a lot shorter list than going from negative infinity to positive infinity and just throwing random numbers out there. So ultimately what this is doing is just trying to narrow our focus down to at least some smart numbers to try with synthetic division, with again my goal being I want to have the final number or the remainder come back as 0. If that happens to be true, then I can then say that particular number was a 0 for that polynomial. And we'll work through one more example here in just a second, where we actually apply this list and go full on through the whole actual factoring of a polynomial, even if I don't give you what one of the factors happens to be. So this last example is the kind of culmination of all of the information talked about thus far. In this scenario, it wants us to find all of the rational zeros and then come up with what this actually is in factored form. So the first thing I would do is list out all of the p over q values that could be here for this problem. So it's going to be the factors of the constant, which would be plus or minus 1, plus or minus 2, and plus or minus 4, all over, and then the leading coefficient, which in this case is the 3, so plus or minus 1 and plus or minus 3. So if I were to list these out and separate it, it looks like I'd end up with plus or minus 1, plus or minus 2, plus or minus 4 if I took every number on top and put it over the 1 that was on the bottom. And do the same thing, put all of those over 3, so plus or minus 1/3, plus or minus 2/3, and the very last one, plus or minus 4/3, are my options. So I'm going to go ahead and just kind of set this up and get my synthetic division on the roll here. So I'd end up with my coefficients 3, negative 11, skips over the x squared, so 0, then my x term 10, and my constant negative 4. So again, I'm just going to kind of, from my list, just do a little bit of trial and error with some numbers, and if they work, cool. If they don't, then I just start over. So I'm going to try the easiest number 1 first. First number drops down, and then I'll multiply and add and continue this process. So I'm going to go through this part relatively quick and just hope that this ends up working out. In this case, it looks like the final result would be a remainder that's not 0, so I'm going to go ahead and try something different. So tried 1 out, that didn't work. We can maybe try negative 1 now. That would be the next easiest number to try. So if I go through and do all of this, I end up with a negative 14 here, positive 14 for the next one, a negative 14 for this one, which would give me negative 4, and negative 4 times negative 1 would give me positive 4. All right, that one worked out. That one gave me a 0 as a remainder, which then means if I were to maybe total these up for part A, it says to find all of the rational zeros. I'm just going to go ahead and start listing them out as I find them. So 1 0 I just found was negative 1. Now once I've divided successfully, what I'm actually going to do is use those new coefficients, so kind of set up a different synthetic division just right underneath it, And now I'll try out some numbers with this one. So let's see, we already tried 1. Maybe let's try 2. So let's try 2 in this one. So 3 would drop down. 3 times 2 would give me 6. Negative 14 plus 6 is a negative 8. A negative 8 times 2, that would be a negative 16. 14 plus negative 16 would be a negative 2. And a negative 2 times a 2 would give me a negative 4. Which in this case, that would give me negative 8 in the end. So that was close. It almost gave me the right number, but in this case it was the opposite. So maybe let's try negative 2 and just see if that one works. So 3 times negative 2 would be negative 6, and negative 20. Negative 20 times negative 2, that gives me positive 40. This already right now seems like that's going to grow and grow and grow and not give me a positive 4 at the end, so I'm going to basically stop at that point and move on to potentially a different number. So let's maybe try 4, positive 4, and see what happens. So 3 times 4 is going to give me a 12. That would give me negative 2. Negative 2 and times 4 would be a negative 8. Add those together. That doesn't seem like that's working. Get positive 6. And 6 times 4, that's going to be a little bit too large. So it seems to me like maybe I should start trying some of the fractions. So let's maybe try that out. Maybe 1/3. 3 times 1/3 would give me 1. Added with that, negative 13. Negative 13 times that. That doesn't seem like that's going to give me something that's going to turn back out of being fractions the rest of the way. So I feel like that's not so great. Maybe positive 2/3. Try this one out. Multiply by 3 times 2/3 is 2. That gives me a negative 12. Negative 12 times 2/3 would give me negative, let's see, what would that be? Negative 8. And that would give me 6. And 6 times 2/3 would be a 4. Alright, that one finally did give me a 0. And what's nice about my result is it technically is a quadratic. Remember though, when I have this fraction inside, I need to divide each of these numbers by that value. So that would give me a 1, a negative 4, and a positive 2. So I can also add on 2/3 as one of my zeros here to the list. But now I should be able to actually factor this, or turn this back into quadratic form, where I've got x squared minus 4x plus 2. That I'm technically trying to set that equal to 0 and solve. So my personal preference with this one, having a b value that was even, is to complete the square. So I'd end up with x squared minus 4x equaling negative 2. So the number I would need to introduce to both sides is the, again, if I'm trying to think ahead to, I want this to turn into x minus the half number squared. If I FOILed that out, I would get a positive 4 that would be missing. So I'm going to add 4 to both sides, which then gives me a positive 2. And now I can square root and solve the rest of the way. So with this one, I would end up with x minus 2 now equaling plus or minus the square root of 2. Then add the 2 at the very end, so I end up with x equaling 2 plus or minus the square root of 2 as my final two zeros. So one of them would be the 2 plus square root of 2, and the other one is its conjugate 2 minus the square root of 2, which hopefully that visual provides a little more reason as to why we end up having those irrational zeros happen in conjugate pairs, and again it happens because of that plus or minus symbol. For part B, it wants us to actually factor this into linear factors, so this would just be, go ahead and take each of these and set it up utilizing those parentheses. So x minus a negative 1 would switch to x plus 1. That would be the factor that corresponds with our first zero. The next zero being 2/3, we could do again that kind of shortcut, move the denominator in front of x, and then keep the numerator after if it's a plus or a minus, depending on if it's positive or negative. So since it was positive, I'll keep the plus. And then the last two are just going to be x minus those zeros in parentheses. So 2 plus rad 2, and the last one minus a 2 minus a rad 2. So I kind of ran out of room with that. Let's see if I can maybe rewrite this a little bit cleaner so it's not as jumbled together. So I'll go ahead and just erase all of that since I didn't give myself enough room. But again, notice I'm just grouping those that have two terms in a parenthesis and just keeping them after the minus sign inside the bigger parentheses. So in this case, 2 minus the rad 2 is the last one. And there we have our factor version, at least down in terms of linear factors, and then we had all of our zeros right here that we utilized to set up those factors. So notice this process can be very time consuming, and you can have a lot of trial and error. As you saw, I ended up trying out however many that didn't work, 3 or 4 different examples that didn't work with the synthetic division. But again, kind of the key idea is once you find one that does work, switch and use those new coefficients in synthetic division, like I did over here on the bottom left. Notice I started with, let's just find one of them, and then I didn't go back and reset using the same numbers. I actually came up with a second synthetic division setup utilizing the new coefficients of the 3, the negative 14, the positive 14, and the negative 4. In doing that, that should then kind of dwindle the power down. So kind of keep in mind the original one, I had a power of 4 on it. Once I divided successfully once, now the leading coefficient would have had a power of 3. Then we want to find another one that works. That way it can turn back down into a power of 2, like we had down at the bottom here, where then it eventually turns into a quadratic that I could then try and solve in some way, shape, or form. Could have used quadratic formula if that was your preference on this one, but this definitely did not factor because nothing did multiply to 2 that adds to the negative 4, which kind of told me I was going to get either irrational or complex zeros for my last 2. Anywho, hopefully this video has been helpful in at least clarifying how the problems in your practice will need to be approached. But if you have questions, just reach out and let me know. Appreciate you taking the time watching the video, and we'll catch you next time.